Okay, go ahead.
Hi, my name is Jeff Mahn. I'm a volunteer docent and educator at the National Museum of Nuclear Science and History in Albuquerque, New Mexico. What I'm going to do with this activity is communicate something about ionizing radiation and how it's detected, and introduce the principles of radiation protection. I'd like to begin with a brief look at some characteristics of matter. So as you see in the first slide here, all matter is made up of atoms consisting of protons, neutrons, and electrons. Classical definition of matter is that it has mass and takes up space. There are generally three physical states of matter that are encountered in nature: solid, liquid, and gas, as shown in this particular slide. Although there is a fourth state of matter called plasma, this is not generally encountered in nature because it only occurs in high temperatures. So matter is subject to three types of changes. The first change we call a physical change, and it involves changes in the internal energy of atoms. So in this case, we're talking about changes of state. So going from solid to a liquid to a gas, or vice versa. These are the kinds of changes that involve changes in the internal energy of the atoms. Second kind of change is called a chemical change, and this involves interactions of electrons in the atoms. What we show on the screen here is the chemical reaction of methane gas, primary component of natural gas, being burned or oxidized to produce carbon dioxide, water vapor, and of course it releases lots of energy. The third kind of change is called a nuclear change. These changes involve changes to the nucleus of an atom. The more commonly known nuclear changes are fission and fusion. Fission, of course, is the splitting of a very heavy atom into two lighter atoms and free neutrons, whereas fusion is the combining of two isotopes of hydrogen to produce helium and a very energetic free neutron, also with the release of large amounts of energy. Both of these reactions, of course, involve huge energy releases in accordance with Einstein's famous equation E = mc squared. So a very, very small amount of mass gets multiplied by the speed of light squared to result in a huge amount of energy being released during these reactions. Now, radioactive decay is also a nuclear change. Radioactive decay is the process by which an unstable atomic nucleus becomes more stable by emitting energy in the form of particles or ionizing electromagnetic waves. The energetic particles and electromagnetic waves released in radioactive decay are called ionizing radiation. The forms of ionizing radiation that we're going to explore in this activity are called alpha, beta, and gamma radiation. Now, these terms were coined by Ernest Rutherford in the early 20th century to distinguish the three types based on their relative penetrating power. Alpha and beta radiation are particles that have mass. An alpha particle is a helium nucleus consisting of 2 protons and 2 neutrons. Beta particle is an electron, but it's an electron that originates in the atomic nucleus when a neutron converts to a proton and an electron. The proton is retained within the nucleus while the electron is ejected. And gamma radiation, gamma rays, are high energy electromagnetic waves. Some of you may be familiar with electromagnetic waves, some may not. So let's take a look at the electromagnetic spectrum. This slide shows the electromagnetic spectrum with radio waves at the low energy end of the spectrum and gamma rays at the high energy end. Of course, gamma rays is what we're going to be looking at, one of the kinds of ionizing radiation that we're going to be looking at here. Between these endpoints in the spectrum, we find visible light, which has been expanded in the lower portion of this graphic to show the different colors. So as you can see from the graphic, we've given names to different regions of the spectrum. For example, microwaves, infrared waves, and ultraviolet waves. All electromagnetic waves can be characterized by their energy, their wavelength, and their frequency, all of which are indicated on this graphic. Electromagnetic waves can also be characterized by their ability to ionize atoms. So in this particular graphic, we show that the electromagnetic spectrum can be divided into two pieces, one called ionizing radiation, the other called non-ionizing radiation. The ionizing portion of the spectrum, we have electromagnetic waves that containing energy sufficient to knock electrons off of atoms, thereby creating positively charged ions, hence the name ionizing radiation. For the non-ionizing portion of the spectrum, these waves have insufficient energy to knock electrons off of atoms, and their interaction with biological material really results in nothing more than a heating type effect. And so you can see in the non-ionizing portion of the spectrum, it includes the visible spectrum as well as all of the frequencies or wavelengths that are associated with all of our electrical appliances, including our cell phones. So alpha and beta particles and gamma rays are called ionizing radiation because of their ability to create ions when interacting with matter. There is one other thing we need to know about ionizing radiation, and that is that we are exposed to it every day of our lives. It's called background radiation. This graphic illustrates sources of our background radiation. Some are natural and some are man-made. The primary natural sources are cosmic radiation, in other words, radiation from outer space. There are many radiation sources in space besides the sun. Second one, terrestrial radiation, is what we get from the Earth. There is a lot of radioactive material in the Earth's crust, such as uranium and thorium, both of which are very, very plentiful. Regarding the internal component of our background radiation, this comes from within our own bodies. It's primarily the potassium-40 in our blood. And as you can see here, the greatest or the largest single contributor to our background radiation exposure is from radon. Now, radon is a product of uranium and thorium radioactive decay. It's also a gas. It's one of the noble gases in the periodic table. Because it's a gas, it seeps up through the soil and gets into the air we breathe, which makes it the largest single contributor to our exposure from background radiation because we are constantly breathing it. The primary source of man-made background exposure is medical x-rays and nuclear medicine diagnostic imaging. Okay, so now let's take a look at how we can detect ionizing radiation. What I have here is what I call an old Geiger counter, or what we call an analog type Geiger counter. It's analog because it has an analog display as shown here. Okay? There's a needle that moves in response to the radiation that's detected by the probe right here. So you would put the probe near a source of ionizing radiation. The internals of the probe would then be displayed or have a display on the meter here. As I say, this is the old type. We still have these around, but they're really no longer used. What we use now are digital Geiger counters, just like this one here. They're about the size of a handheld calculator. Okay, so in this case, for the digital Geiger counter, the window for the detector chamber is right here. It's a little circular opening on top of the Geiger counter with a little bit of a grid inside of it. Now, this Geiger counter also has two switches. The top switch actually gives you options for the display, digital display right there. We're going to put it in the bottom position called total on this because all we're interested in is the total counts on the display here. The bottom switch is the on and off switch. It also has a third position called audio, and the reason for this is so that when you're detecting radiation within the Geiger counter, you not only get a digital display here, but you also get an audible signal. So I'm going to turn the Geiger counter on. There's a momentary delay, and then it begins counting what we call background radiation, okay? Question is, what is it actually counting in terms of the background radiation? And you can see the background radiation level is very, very low. What it's actually counting is the decay of radioactive radon in the air we breathe, because right now what's getting inside the chamber is air, and in the air is radioactive radon. So every time one of those radioactive radon atoms decays, it's counted on the display here, and of course you can also hear it. All right, so as I said, following a brief delay when you turn this on, it begins to count background. Now, one of the other things that I want to note before I move on here is that the count rate that, or the number of counts that shows up here, the rate at which those counts appear and you hear them, varies in both time and space. In other words, background radiation is not constant in either time or space anywhere in the world. It varies with time. Okay, so now we're going to take a look at some characteristics of alpha, beta, and gamma radiation using this Geiger counter. First source I'd like to look at is this little item right here. This is called an alpha source, okay? And you probably don't know what this is, but it turns out it is the internal workings of your home smoke detector. This is what makes your home smoke detector work, okay? Behind the circular aluminum piece with the hole in the middle is an americium-241 source. Americium-241 is an alpha particle emitter. So when I turn the Geiger counter on and I bring this alpha source right up close to the window, you can see the count goes crazy, and you can hear it as well. These are all alpha particles coming from the decay of americium-241 entering the chamber and being detected by the Geiger counter. Okay, so let me then take this source, put it next to the window, and slowly move it linearly away from the window. And what you can observe along with me is a very drastic reduction in the number of the count rate, okay? And the reason for this is that these alpha particles have a range in air of only about 1.5 inches. So once I get beyond 1.5 inches from the window, the alpha particles are no longer being counted, entering the chamber and being counted. The reason for this is the alpha particles are interacting with molecules in air to deposit their energy. And in 1.5 inches of air, they deposit all of their energy, and there are no energetic alpha particles left to enter the chamber to be counted. Okay, so next thing I want to do is I want to take this piece of cardstock, which you can see here. Okay, it's very thin, not quite the thickness of an index card. And now what I want to do is insert this piece of cardstock between the window and the alpha source. And as you can hear, again, there's a drastic reduction in the count rate. In other words, the cardstock can be used to block alpha particles. What happens here, of course, is that the alpha particles interact with the atoms in the cardstock, depositing their energy before they get to the window of the Geiger counter. Okay, last thing I'd like to do with the alpha source here is just to show you that when I put my fingers between the source and the window, you can see that alpha particles don't penetrate the human body. Well, if they don't penetrate the cardstock, they obviously don't penetrate the human body. But again, just to show that alpha particles cannot penetrate the human body. Okay, good enough. Next thing I'd like to do is look at a beta source. What I have here is a beta tube. In the green end of this beta tube is a 0.1 microcurie strontium-90 source. Strontium-90 is a beta particle emitter. Okay. So again, when I take this source and I put it up next to the Geiger counter window, then you can see the count rate, and you can hear it going berserk, because all the beta particles coming from the strontium-90 decay are entering that chamber here and being detected. Okay. Now, again, what I'd like to do is move this beta source slowly linearly away from the window, and as you can hear, the count rate decreases. Continues to decrease as I move the source further and further from the window. Okay? Now, these beta particles actually have a range in air of up to 5 feet. Okay? But the reason that there's such a drastic decrease in count rate as I move this away within even a foot of the Geiger counter window is because of the conical angle of the beta particles that enter the chamber to be counted. That conical angle gets smaller and smaller and smaller as I move the source further and further away. Now, this isn't actually a point source, but for all practical purposes, we can treat it as one. And at the end of this, I will give you a little bit more information about what this conical angle and the decrease in count rate as a function of 1 over r squared means with distance. But for right now, I won't go into it further. Okay, so let's go back to putting the beta source up close. Now I want to take this cardstock again, and I want to insert it between the source and the window. And as you can hear, there's no difference in the count rate. Okay? So this cardstock is insufficient to block beta particles. Now let me take this thin sheet of lead, see how thin it is, okay? And let me insert that between the beta source and the window. And now, as you can hear, the count rate has been drastically reduced again. So this thin sheet of lead is sufficient to block beta particles. Actually, any thin sheet of any metal will be sufficient to block beta particles. Doesn't have to be lead, it can be any metal. Okay, so last thing I want to do with this beta source is again show by putting my hand in here that beta particles, again, do not penetrate the human body. The count rate is essentially background with my hand between the source and the window. Okay, so what I would like to note from this is that as external sources of alpha and beta radiation, sources of alpha and beta radiation, external sources, are not health hazards because they can't penetrate the dead layer of our skin. Therefore, they cannot get into our internal body parts and organs to have any effect. Okay, let's take a look now at gamma source. This is a gamma tube, and one of the museum's radiation sources. And the orange end of this tube is a 1 microcurie cobalt-60 source. Cobalt-60, when it decays, results in 2 gamma rays being given off. So, again, let me turn the Geiger counter on. And once it starts counting, I will bring the gamma source near the window, right up against the window. And as you can hear and see on the display, it's detecting gamma rays and counting them. Okay? All right. Now, again, what I'd like to do is show by slowly moving the gamma source away linearly from the window of the Geiger counter, you can hear the count rate decreases and decreases to the point where it sounds like it's really nothing but background at this point. Again, what we're looking at here is the decreasing conical angle for the particles, or the gamma rays, excuse me, being emitted from the cobalt-60 source, which again can be, for all practical purposes, considered to be a point source. Okay, bringing the cobalt source back near the window, and now I'm going to take this thin lead sheet and put it between the source and the window, and as you can hear, it really makes no difference to the count rate. Okay, so this thin sheet of lead is insufficient to block gamma rays. Now, it turns out we do use lead to block gamma rays, but we use very, very large thicknesses of lead. In other words, we make bricks out of lead that can be piled next to each other and stacked on top of each other to block gamma radiation, and we use whatever we need depending upon the source strength of the gamma radiation to block it, so it either doesn't get detected or we don't get exposed to it. Okay, last thing I'd like to do again is to show that in this case, if I put my hand between the source and the window, as you can hear from the count rate, the gamma rays do penetrate the human body. Okay? They are like X-rays. If you refer back to the electromagnetic spectrum, if you happen to notice, gamma rays are the high energy end, and right below gamma rays are X-rays. They're somewhat lower in energy and a little bit longer in wavelength, lower in frequency. But gamma rays and X-rays have similar properties in terms of what they can do in being used for imaging internal body organs. Okay, let me take up one other issue here, which you may have noticed and probably have had a question about. This cobalt-60 source, as I mentioned, is 1 microcurie source. This strontium-90 source is a 0.1 microcurie source. So the cobalt source is 10 times the strength of the strontium-90 source. Yet, when you listen to the count rate, there's a rather drastic difference in count rate between the beta source and the gamma source. Okay? But even though the gamma source is 10 times the strength of the beta source, it is registering a lot fewer counts in the Geiger counter. Why is that? Okay. Well, as I indicated, gamma rays can penetrate the human body, just like X-rays. Turns out that when I bring this in the vicinity, the gamma ray source in the vicinity of the Geiger counter, the vast majority of the gamma rays go right on through the Geiger counter without ever interacting with the internals of the detecting chamber, and therefore they don't get counted. Okay, just like they can penetrate the human body, they penetrate this Geiger counter without ever interacting, which is why the count rate on the beta source and the alpha source is so much greater, because all of the beta particles or all of the alpha particles that enter the chamber get counted. Whereas all of the gamma rays that enter the chamber, or let's say most of the gamma rays that enter the chamber, go right on through without ever interacting and therefore do not get counted. Hope that makes sense. So, as I mentioned, regarding external alpha and gamma ray sources are not really biological hazards because they can't penetrate the dead layer of our skin. As an external source of radiation, a gamma ray source may be a health hazard depending upon the source strength. Now, what about the source strength? When I do this activity with school kids, I generally pick up this at the end of the session and ask them, is this source dangerous? And some of the kids will respond yes, some will say no, and I will then respond, if it were dangerous, we wouldn't let them play with it. Turns out that this is a very weak cobalt-60 source because there's so little cobalt-60 in it. So if I played with this source for the next 24 hours at a distance of 1 foot from my body, the total dose that I would get from this in that 24-hour period would be only about 1/3 of what I get on a daily basis from normal background radiation. Okay? So you can see this is a very, very weak cobalt-60 source. Okay, so let me go back to slide here. And now I'm going to talk about the radiation protection principles. First one is called time. We want to restrict our proximity to any ionizing radiation source to the smallest amount of time possible, because the total dose obviously is equal to the dose rate times the time. So that is the first principle. The other two principles, the second and third, we have demonstrated in this activity. Second one being shielding material. Shielding material that we used in this case was the cardstock or the thin sheet of lead. Radiation is effectively blocked by dense materials. So you always want to use appropriate shielding material and as much as needed to block whatever ionizing radiation is necessary to minimize your dose. And the third principle is distance. As I showed with these sources, as I move them linearly away slowly from the window of the Geiger counter, the count rate went down. Okay, the count rate or the dose actually decreases as we call 1 over r squared. Now, what does that mean? Glad you asked. Let's take a look at that. Okay, and this one last graphic I got here is anyone who may not be mathematically inclined to understand what is meant by 1 over r squared drop off in radiation exposure as the distance is increased between the radiation source and the object being exposed. So, as I said, with both the beta tube and the gamma tube, these aren't really point sources, but we can, for all practical purposes, consider them as such. A point source emits radiation in a sphere. So as the distance from the point source is increased, the radiation spreads out. Note the spreading as the distance in the graphic is increased from r to 2r and 3r. For an exposed object of fixed dimensions, there is a particular conical angle at distance r from the point source that contains all the radiation to which the object is exposed. And in this case, if you take a look at the rectangular surface area on the sphere at radius r, that's the fixed dimension object I'm talking about here. Okay, now as the object of fixed dimensions is moved to a distance of 3r from the source, the amount of radiation to which the object is exposed gets smaller. That is, a lot of the radiation contained within the conical angle for distance r is now outside the dimensions of the object. Yeah, so as shown in the graphic, at a distance of 3r from the radiation source, the object of fixed dimensions is exposed to only 1/9 of the radiation it would be exposed to at a distance r. So as the distance from the source is increased by a factor of 3, the radiation exposure is decreased by a factor of 9, or 3 squared. This inverse squared relationship between the exposure, or dose, and distance is commonly referred to as 1 over r squared. So I hope that makes a little bit more sense with respect to what I was talking about with the beta and gamma ray sources decreasing their count rate as a function of 1 over r squared. So that is the end of this activity. I would like to thank you for your time. I hope this activity has been informative, and I hope I have been effective in communicating the fact that ionizing radiation, when properly understood, does not need to be feared. Thank you.